Here we are again, already to chapter 3. And today we're going to be talking about basically serial. They're calling it point-to-point, but we know point-to-point is serial, and finally it explains why we draw a cable like that, right? And so that drawing can do a lot of things, but typically we're setting it on on our old serial links. And why we're doing that is because, well, if you're unlucky, they're still used, but, or I guess if you're kind of lucky, I don't know, if you like that kind of thing, it's great. But anyways, this is lease line technology, and so there's some different things we can do, and the reason we still study a lot of this is PPP, then functions in over Ethernet, and is used with DSL quite often. But we'll be getting to that when we do. So we're going to explain the fundamentals of point-to-point serial communication across WAN, configure HDLC encapsulation on point-to-point serial link, describe the benefits of PPP over HDLC in a WAN, describe PPP layered architecture and functions of LCP and NCP, explain how PPP session is established, and configure PPP encapsulation on a point-to-point serial link, configure PPP authentication protocols, use show and debug for troubleshooting PPP. Okay. So, serial and parallel cables, alright? So, we have that. What's the difference between a serial and parallel? Well, parallel sends all at the same time. It's older. What else do we need to know about? Oh, what else you need? I don't know. Theoretically, a parallel is faster, but the wires are all together. It's a dead technology. Maybe some of you guys remember that our computers used to have both serial and parallel, but now some of them still have serial, some of them don't. And that's because they were replaced with USBs. But for long distance communication, WANs still use serial transmission. Sure they do. And so whenever we say this is just a straight lease line. Alright, so we have some different types of serial. So we have RS-232. Most serial port on a personal computer conform to the RS-232 or the newer RS-422 and the RS-423 standards. Both 9-pin and 25 connectors are used. A serial port is a general purpose interface that can be used for almost any type of device, including modems, mice, and printers. These types of peripheral devices for computers have been replaced by new and faster standards such as USB. V.35, typically used for modem to multiplexer communication. This ITU standard for high-speed synchronous data exchange combines bandwidth of several telephone circuits. In the US, V35 is the interface standard used by most routers and DSUs that connect to T1 carriers. A V35 cable are high-speed serial assemblers designed to support higher data rates and connectivities between DTEs and DCEs over digital lines. There is more on DTEs and DCEs later in this section. HSSI, a high-speed serial interface, supports transmission rates up to 52 meg. Engineers use HSSI to connect routers on LANs with WANs over high-speed lines such as T3 lines. Engineers also use HSI to provide high-speed connectivity between LANs using token ring or Ethernet. HSSI is a DTE-DCE interface developed by Cisco Systems and T3 Plus networking to address the need for high-speed communications over WAN links. Alright, so our serials connect to the CSU DSU. Is that what we're talking about here? I don't know. I'm not really sure what they want here. Connect 2 points geographically. Alright. So once again, we talked about this last chapter. These routers think they're directly connected even though they're going over a WAN, long distance, right? Like New York to London. That's a long ways. But these routers believe that they're connected just through basically one switch. That's the beauty of these WAN connections. The cost of leased line solutions can become significant when used to connect many sites over increasing distances. However, there are times when the benefits outweigh the costs of a leased line. The dedicated capacity removes latency or jitter between the endpoints. Constant availability is essential for some applications such as VoIP or video over IP. So what they're saying is if you use some T3s, you'd probably still be, good here. And where it's really good is where we'd probably use a lease line is if everything we design is proprietary and we have to share it between offices. We don't want a chance of it being intercepted or if it's top secret. And so because of that, we have to use a lease line. Yep. Anyways, and so now we've heard about this TDM, right? It was back in CCNA4, but we're going to find out what it actually means right now. Remember, some of these WAN technologies we are no longer using TDM with, right? So TDM is a type of multiplexing. It stands for time division multiplexing. Bell Laboratories originally intended TDM to maximize the amount of voice traffic carried over a medium before multiplexing. Each telephone call required its own physical link, blah blah blah. So basically, it separates it into a time sequence. But then we have, let's see, do we have STDM over here? Yep. Then, so this is what they would use then, because if we're just doing each time slot, and say one of these devices wasn't sending, then we're just wasting that. And so what STDM does is it still uses the time slots, but say if E isn't using, or like as we can see here, somebody wasn't using their time slot, it would be probably D, right? And so E used, or F used both time slots, and here E didn't. So before, if we look here, they're completely, in sync. But what if one wasn't sending? Then we're just wasting that bandwidth, and so that's what STDM changed. On largest blah blah blah. So what's important here is SONET's using STDM. So the figure displays SONET, which is an example of STDM. SONET takes the N bit streams and multiplexes them and optically modulates the light signals. It then sends the signals out using a light emitting device over fiber with a bit rate equal to incoming bit rate times N, thus traffic arriving at a SONET multiplexer from 4 places at 2.5 gigabits goes out as a single stream at 4 times 2.5 gigabits or 10 gig. This principle is illustrated in the figure, which shows an increase in the bit rate by a factor of 4 in the time slot T. Alright, so basically we have these different streams broken up, right? These could be different clients or whatever, different ISPs, and then they hit the 10 gig pipe as one and can be then broken down again, right? That's basically what it's trying to say. Anyways, you're not going to be testing much on that, so don't fret. But it's a good thing to know. All right, our demarc point. I can't say the full word, so I just call it a demarc. And so what the demarc is, right, is where we talked about this last chapter. This is where either we have to fix it or the ISP has to fix it. We control this side, or if you're working in IT department, you control this side. And apparently it's different on in international. They control your CSU, DSU, or I guess they call it NTU there. Anyway, so they control that, so it's, you just are responsible for what's going in your router. So if you work for the ISP, you'd have to fix it if it's on this side. You just test to this side, and you say, hey, this all looks good. It's your responsibility, and that's all it is a contract responsibility. And this is just a module that has the CSU, DSU embedded into it, so you can just run a straight cable into it and plug that into your router instead of having. They used to make these were another device. There are some in the classroom if you look around. So just to show you, they're not common. But actually, what these did is a serial cable, like the V35s, would plug into one side, and then a copper cable would come out and just go into a LAN interface on the other side, or a T1 interface. Not a T. Well, yeah. That's as far as I'm going to go, because you're probably not going to see those. Here we go. The DTE, DC is the controller. Okay, this thing's setting the bandwidth. It is on the provider is controlling this, right? And it's going to set our clock rate. With serial cables, we have to set a clock rate. We had a speed on Ethernet, right? Like your 1 gig or whatever. Our clock rate determines what our speed is, and it's only on one side because they're synchronous, but it's the data communications. If you want an easy way to remember, DCE means controller, right? It's going to set a clock rate, or the data clock, all right? And then the DTE termination, that's the side the client plugs in, but it is not, you cannot set a speed on the DTE end. So every serial cable has a DCE and a DTE end. So, hope that makes sense. So here we go. The CPE, which is generally a router, is the DTE. This is customer presence equipment, right? DTE could also be a terminal, computer, printer, or fax machine if they connect directly to the service provider network. The DCE, commonly a modem or CSU/DSU, is the device used to convert the user data from the DTE into a form acceptable to the WAN service provider transmission link. This signal is received at the remote DCE, which decodes the signal back into sequence of bits. The remote DCE then signals this sequence to the remote DTE. Alright, so then we have our serial cables, right? And I don't know, how much do we want to talk about? Alright, so this is just a long explanation of that a typical cable is DTE to DCE. Alright, and basically all this thing is saying, if you're looking, what it's going to do is it crosses over, so we can connect we can connect one DCE end to a DTE end to a similar device pretty easily. But if we're going to use two DTE ends, it takes a special cable that has to be rewired. Like we can't take a DTE side that's wired for a DCE, because we can screw these together, right? Let's see if they have them like this. Let's see, is that the best thing? Like this side with this side, right? So we have DTE has the pins, DCE doesn't, and so we can't take, as you can see, a DTE with a DTE. It's called a no modem cable if you do that, and it's used for, it used to be used for programming serial and, I don't know, like IBM devices and that kind of thing. Sometimes you still need one. Very few devices these days. And most of them run over the rollover cable or something like that. But yeah, so we have our old RS-232 right there, right? And then here's our different standards, right? V35, X21. I don't know where these are important. This is our newer version, right? Which I believe is it's the Cisco one, I believe. Anyways, once again, this you're not gonna be tested on this too much. Only thing you know, DC sets clock rate. It needs to have a clock rate. Here it is. This is a smart serial. Why can't I think of that? So this is a smart serial. And if you look here to support higher port densities, this is a lot smaller than plugging in a bunch of those, which were the big ones at. They don't even have any big ones here, but they used to be big. They're in the classroom if you want to see them. Anyhow, great stuff here on the serial. So, serial bandwidth speeds. Here you go. So let's list the different speeds, and I don't know. These ones right after this, these are all optical, so they're not serial. They're not coming in through copper, right? They're coming in through fiber, and they're SONET, so I don't consider them serial. Anyways, you can read about that there, but it's pretty interesting to see our different speeds. OC 768, 39.813 gigs. That's pretty nice. Oh yeah, and so the opposite of T1 in Europe, they call them E. So E1, E3. So now to encapsulation. So remember, all of these are layer 2 encapsulations, right? So we're used to Ethernet, but serial doesn't run over Ethernet. Serial has some options. HDLC and PPP are the ones we care about. SLIP is something else. So HDLC, the default encapsulation, so that's why we never see it. But if we just plug in two serials, that's what it's running off by default, is HDLC. Dedicated links and circuit switch connections. When the link uses two Cisco devices, HDLC is now the basis for synchronous. PPP, used by many servers, connect to the WAN, most commonly the internet. PPP provides router-to-router and host-to-network connections over synchronous and asynchronous circuits. PPP works with several network layer protocols such as IP version 6, IP version 4. PPP uses HDLC encapsulation protocol, but also has built-in security mechanisms such as PAP and CHAP. SLIP, Serial Line Internet Protocol, a standard protocol for point-to-point serial connections using TCP/IP. SLIP has been largely displaced by PPP. X25, an ITU standard that defines how, basically this was what frame relay was before it was frame relay, and then we have frame relay, an industry standard switch data link layer protocol that handles multiple virtual circuits. Frame relay is a next generation protocol. X25 frame relay eliminates some of the time-consuming processes such as error correction, flow control employed by X25. And then we have ATM, the international standard for cell relay, in which devices send multiple service types such as voice, video, or data in fixed length 53 byte cells. Fixed length cells allow processing to occur in hardware, thereby reducing transmit delays. ATM takes advantage of high-speed transmission media such as E3, SONET, and T3. Okay, so HDLC, that's its, Cisco has its own version of HDLC, and as you can see, it has a protocol field in it. The protocol solve the inability to provide multi-protocol support, right? So that's going to be our layer 3 information. Anyways, here's the standard. This is it. This is our default. So you'd have to turn off the default if you're running with a non-Cisco, though, because Cisco HDLC is Cisco proprietary. Mostly you just need to know that it's the default serial on serial encapsulation. If you want to read about all the stuff, it's similar to our Ethernet, except since these are point-to-point or address, it's usually just a destination address. Let's see if that's right. Doesn't even have the address on here. I don't see it, at least. Anyways, oh, here it is. The address contains the HDLC address of the secondary station. This address can contain a specific address, group address, or broadcast address. Primary address is either a communication source or a destination, which eliminates the need to include the address of the primary. Anyways, take a look at that. How do we set it up? We normally don't see this because it's already set, but we do just go into our interface, encapsulation, HDLC, right? Pretty easy. Troubleshooting the serial, 2 commands. I usually don't do show interface serial. It doesn't show us a lot. I guess it shows us our encapsulation and the protocols are important. But show controllers, I do this in its huge page. And if you do show controllers without the interface, it does all of them. But what we're looking for in the serials is if we don't know if an AND is DCE or DTE, this tells us. Probably not a common thing, but shows us our DCE, and remember the DCE sets the clock rate, and we can see that there as well. Syntax checker, you guys can go over that. So now we have PPP. Okay, so PPP contains 3 main components. HDLC-like framing for transport multi-protocol packets over point-to-point links. It has extendable link control, LSCP, for establishing, configuring, testing the data link connection. That's probably one of the major, these 2 things are the major reasons we like NCP. And then it has NCP for establishing, configuring different network layer protocols. PPP allows the simultaneous use of multiple network layer protocols. Some of the more common NCP internet protocols are IP version 4, IP version 6, control protocol, all those have control protocols, AppleTalk, Novell, control protocol, Cisco Systems Control Protocol, SNA, and it actually passes Cisco Discovery Protocol over it too. Control protocol. So, advantage of PPP. Well, because 1, we have authentication, and 2, probably link quality management. That's the main. So link quality management feature shown in the figure monitors the quality of the link. Too many errors are detected, PPP takes the link down, right? So it kind of gives us a IP SLA feature kind of thing where we're monitoring what we're actually getting. PPP supports PPP and CHAP authentication. This feature is explained in practice later in the section. So basically we can authenticate. That's all it's saying. We can use a username to sign in here and here. It's not just on, right? So we can secure ourselves. So here's what the NCP is doing, right? So LCP runs, we're going to see a section on this here pretty quick, but NCP runs the authentication, and it's checking the quality and doing all that, and then it hands it off to NCP, and NCP takes care of the top layer protocols. I think of it as it's kind of like our on our Ethernet, our let's see, our LLC is handing off to the upper layers, right? Which it works with 2 and 3, right? It hands off to the upper layers, and then the MAC sublayer works with down here and make sure it does the addressing, but it also allows us to use different types of media. It works with the hardware, and so I think of this in the same way. LSCP is the hardware, NCP is taking care of our upper protocols, our software drivers with our devices. Okay. So on the physical layer, you can use asynchronous, serial, synchronous, HSSI, and ISDN. So here's our LCP. So what LCP provides automatic configuration of interfaces at each end, including handling varying limits on packet size, detecting common misconfiguration errors, terminating link, determining when a link is functioning properly or when it is failing. After the link is established, PPP also uses the LCP to agree automatically on encapsulation formats such as authentication, compression, and error detection. Okay, so that's all these things are the important things about LCP, but probably the questions you're going to be asked is what's handling authentication, compression, and error detection? Well, that's the LCP. And link quality would be on there too. Then we have the NCP. NCP just negotiates with the layer 3 protocols and hands them off. Here's some NCP protocols. We'll have some shows that will make these have more sense. Whenever we establish a PPP, we can do a show. I don't know. Show PPP. I don't remember what the command is, right? Show. I don't know. Now show interfaces. Well, it'll show what's actually negotiating going, I believe. I don't know. We'll see it here in a second. Alright, there's our PPP frame. You can compare it to HDLC or Ethernet if you want. Good stuff to know. Okay, so this one's important. You'll be tested on this chapter or on this test. So how does PPP establish a session? First, link establishment before PPP exchanges any network layer stuff, right? What's it do? LCP. Okay, so LCP must open the connection and negotiate configuration options. This phase is complete when the receiving router sends a configuration acknowledgement frame back to the router initiating the connection. Then we can do link quality. If we have this enabled, the LCP tests the link to determine whether the link quality is sufficient to bring up the network layer protocols. The LCP can delay transmission of network layer protocol information until this phase is complete. So until our line is good enough to handle the traffic, it will not come up. Then after that, it hands off to NCP, and the appropriate NCP can separately configure the network layer protocols and bring them up and take them down at any time. If LCP closes the link, it informs the network layer protocols so that they take appropriate action. Alright, so once again, I believe you have a drag and drop or something on this. Right, so LCP configure request, LCP acknowledge, NCP packet exchange. Unless then after we're established, right, that's the initial. Apparently we go to right here. I don't know what to really tell you about that it's not showing you, so just look over those over what's going on there. Basically it's just data exchanged with ping. Apparently a ping came across, right, and then we had our data exchange. Then if we want to terminate, just a two-way, the LCP terminate request, probably because after the transfer of data, the network layer completes, the LCP terminates the link as shown. NCP only terminates the network layer, and the NCP link. The link remains up until LCP terminates it. If LCP terminates the link before NCP, the NCP session is also terminated. Alright, so I don't know where that's important, but hey, good stuff, good stuff. So we saw our frame, now we see our NCP packet, which is inside of our PPP frame, right? And yeah. What else do we have here? Oh, we have authentication. Oh, our other options. Authentication, PAP and CHAP. We can compress it so it kind of zips it as it comes across. Or we can bundle this in another place. If we can only get T1 somewhere and we need more speeds, we could take several T1s, use a multi-link bundle, and bundle them together to work as one. Which apparently is in our LCP variables, alright? Yeah. the NCP process. What do we want to talk about? This is okay. So IPCP, if we do a show on these, anything that's CP, we know that's NCP. So if we see some CPs, we know that our LCP was successful in bringing the link up and it's handed off to the NCP. And so apparently IPCP negotiates two options, allows devices to negotiate an algorithm, compress TCP and IP headers, and save bandwidth. Okay, great. And it gives us addressing. Neat stuff here. Go ahead, do some of those configuring, because they have a lot of really hard test questions. Alright, so another PPP configurable options. We can configure it to run with PAP or CHAP. We're always going to configure CHAP because PAP is in clear text, it's worthless. Pretty easy to configure. I think we'll get there in a second. Protocol compression. We can compress it. We can program for compression. We're just going to say that. Address and control field compression. More QoS. Magic number detection. This is a random chosen distinguish appear and detect looped back lines. So I would guess this is probably used in bundling. I don't know. And then let's see, does it say anything more about? Oh, it has our configuration commands down here for callback. Callback PP. This is a good one. PPP callback is used to enhance security. With the LCP function, a Cisco router can act as a callback client or a callback server. The client makes the initial call or request. The server call it back and terminates its initial call. The callback router answers the initial call and makes it return call to the client based on its configuration statements. Alright, so what that's doing is making sure who it's talking to is the right person, right? This alternative, our multi-link, allows balancing over the router interfaces the PPP use. Multi-link PPP, also referred to as MP, MPPP, MLP, or multi-link, provides a method for spreading traffic across multiple physical WAN links while providing packet fragmentation and reassembly, proper sequencing, multi-vendor interoperability, and load balancing on inbound and outbound traffic. Basic PPP, similar to HDLC, except it's not the default, so we just say encapsulation PPP. Now if we do that on one side, it's going to take the other side down, right? Because when we're initially doing this, we have to do it on both sides or it won't come up. Because one would be on PPP, one would be on HDLC. How do we compress it? Right here. So I don't know. You guys are not going to be tested on this, but you can use the compress command. And so what's probably important is if the traffic's not linearly compressed with a zip tar or MPEG, it does not use this option. So let's see. It involves software compression. It can affect system performance. But basically we can put in the predictor, which is optional. We can just say compress, I believe, and just press enter, or say predictor on both sides, or I don't know, whatever stacker is, different algorithm. Okay, so we can choose either one of those. PPP quality, we put in a percentage. This percentage means that we should get, if we aren't getting 80% of our bandwidth, it'll take the link down. Our multi-link, alright, we make a virtual interface, multi-link, and a number, right? PPP multi-link, PPP multi-link group 1. It's similar to like our Ether channel, except, yeah, up here. So we program it all in. then we don't put the IP addresses on our serials and we assign them to the group 1, just like, which is identified up here. Okay, and that gives them the IP address. It's very similar to our Ether channel configurations. Troubleshooting, show interface serial. What we're looking for is encapsulation PPP, LCP open. Okay, if we didn't see these LCP open and these not, it would mean that we have some LCP errors, right? This shows that we're passing NCP as well. And there are our show commands, show interfaces serial. Or we can show our multi-link. I've never used multi-link, so take what you want from here. And you won't be tested on it, hopefully, too much. Alright, so PAP, we're not even going to talk about it because it's worthless. But PAP just sends password clear text, right? Sends it, right? We program it on the interface, say, hey, throw this password out there. And then CHAP, it does a 3-way handshake instead. It does a challenge. And then this guy sends a hash with a username with the hash, and either it's accepted. So they actually have a 3-way handshake and it's encrypted rather than just clear text sending across. That's why PAP is basically dead. So globally, we say PPP authentication PAP. I believe it's globally. Let me make sure. So I have it right here. Yeah, I'm pretty sure it's at the interface. Alright. Yeah, let's just get to the programming. Here we go. Alright, so okay, so I was wrong. It's not at global. It's in the interface. We say encapsulation PPP, then we say PPP authentication, choose CHAP or PAP, or both of them. I'd always just use CHAP. Then with CHAP, we make a username on the outside, and we make it for, we would make it for this router. The username would be R1 with the enable password, or the enable secret password as the password for that username here, and it would be vice versa over here, right? And then they would work, right? So we made the username of R1 with the password CHAP authentication, so we just have to make a username and enable CHAP authentication inside of the interface. Otherwise, we could use our AAA, which would be TACAX or Radius. I would guess we could use Radius with this too. Yeah, it says, I would guess this AAA would actually support Radius, but that's a little past where that's more of a CCNA4 question. So, anyways, here it is. There's our PAP, and so in the actual interface, as you guys can see, hopefully, we have the password, the username and password we're going to send to the guy, which again is going to go in clear text across service providers, so it's a bad idea. Go ahead and give it a try here. Then with CHAP, notice we just made a username and enabled CHAP. Okay, and so not only is it less commands, it's just way more fun. Okay, so and encrypted. So go ahead and try that there, or try the packet tracer. What else do we have left here? Troubleshooting. So if PPP, if we're having LCPs not working, something like that, we can do debug PPP packet, negotiation, error, authentication. We can try any of these depending on where we think our error is happening, and it's going to bring a lot of things out. Again, another warning with debug, remember if you do a debug all, you're going to crash your router. Debug PPP, you want to take this off after a while because every little thing is coming through, and it could max out your CPU. Let's see, so debug PPP packet. This is what you're going to see, right? And what you're looking for is, I believe this is the one, let's see. No. PPP negotiation. PPP packet, this would just be showing us the stuff from, if we look back to our PPP packet, it's going to show us all the information. No, I'm not going to go there. But if you guys want to go back in the chapter, it'll show what's coming across in our, oops, went too far. Okay. It'll show what's coming across in our PPP packet, our PPP negotiation. We want to see these confirms coming through, and making sure everything goes up and opens right. And you guys can look through here. Challenge went across. We want to make sure the password goes through right. All that. PPP error. I don't know. I guess that's just showing you like frame errors or something on there. I've never used that one. And then we have debug PPP authentication. It's going to tell us if CHAP or something isn't working right, and it's just going to go through and give us errors. So those are our debug commands. Okay, you're going to have some hard test questions on this debug for no apparent reason. So I strongly suggest using the troubleshooting with PPP, troubleshooting PPP authentication, and maybe this lab, so that you are familiar with the debug commands and how PPP works, or just read through every little detail, because there are some really tough questions on PPP on this test. But that is the chapter, and I don't know. I probably was a little rough on some parts, so you might have some questions. Go ahead and send me an email if you do.